In Chapter 6, we will be looking at organic reactions and how they work. The image that you're looking at here is the crystal structure of protein kinase A, which catalyzes the phosphorylation of different amino acids inside of proteins. So we might have some generic amino acid, which we'll learn about later on in the semester, and we have something called ATP, which is adenosine triphosphate. It has 3 phosphate groups, and one of those, by this enzyme that's shown here, the protein kinase A, is going to transfer that phosphate group onto where that OH group is. So these chemical reactions happen all the time in the lab and in nature, and they follow the same rules, and the functional groups will react similarly. So it's important to be able to recognize functional groups, recognize the patterns of these reactions. That way we don't have to focus on memorizing every single specific reaction. There are 4 types of reactions that we're going to cover in this class. The first of which is a functional group transformation, or an FGT, and that's going to be a change of one functional group to the next. We're also going to look at reactions where carbon-carbon bonds are formed. We have reductions and then oxidations. So in a functional group transformation, one functional group changes into another. So in the reaction of bromocyclopentane, that bromine is going to change to an OH group, and then we get sodium bromide as a byproduct. And if we have an alkene, we add water in the presence of acid. We're going to change the alkene into an alcohol. So this is one functional group that gets converted into another. In a carbon-carbon bond forming reaction, as the name implies, we're going to form a new bond between 2 carbons. So in the case of chloropropane, I'm going to form a bond to this Grignard reagent, or this MgBr. So these 3 carbons are getting added here, 1, 2, 3, to form a new bond there. And then we have a ketone, and we add this Wittig reagent to it, which we'll learn about later on. And we form a new carbon-carbon bond. So these are the new bonds that are formed in these carbon-carbon bond forming reactions. In a reduction reaction, we're going to gain hydrogen. This often happens across a double bond, but if you remember our oil rig, oxidation is loss of hydrogen, reduction is gain, and we're looking at the rig part of it here. So in the reaction of propene with H2, or hydrogen and palladium, we're going to add 2 H's across this double bond, and for this ketone, we'll add H's across the double bond to form an alcohol. An oxidation is the loss of hydrogen, so that oil rig is oxygen is lost. We can also think of it as being a gain in CO bonds. So if I have an H here, I oxidize it using sodium dichromate. I'm going to lose the hydrogen, and we're also gaining a CO bond with PCC. That hydrogen is going to get lost. And we're going to gain a CO bond here, as well as lose the hydrogen. And in this case, with the sodium dichromate, I gain a CO bond to form a carboxylic acid. Organic reactions work via reaction mechanisms, and this is the overall description of how a reaction works. We're dealing with the bond making and the bond breaking. In radical reactions, electrons are moving 1 electron at a time. And in polar reactions, we're moving a pair of electrons at a time. So in this case here, we have an A plus B that forms from the split. 1 electron is here, 1 gets moved here. And in the case of this AB, with the polar reactions, the pair of electrons is going to go on to B. This results in a charged A, where it's positive, where it lost its electrons. B now has an extra, so it's negatively charged. So with radical reactions, we have a symmetrical bond breaking, and one of the atoms each gets an electron. And in the unsymmetrical, or these polar reactions, the two electrons stay together and they go on to one product. Radical reactions are highly reactive. As we mentioned in the last slide, they involve single unpaired electrons. So in this radical reaction here, we have an unpaired electron. One of these electrons from the AB can come to join up with this radical, and one goes on to the B. So we get this unpaired electron, and then the rad A forms the new product. We can also have this unpaired reactant radical, and one of these electrons from the alkene can form a new bond there. And then that goes on to the carbon. So we get this radical that forms and a new bond to the rad. So this is an addition radical product. There's 3 steps to radical reactions. So in the reaction of methane plus chlorine, which is initiated by light to form chloromethane, the first step is the initiation reaction. This is where the reaction starts with UV light or heat in order to form the radical. It's then propagated, where radicals can react with another radical. And then when 2 radicals come together, that will complete the reaction in the termination step. So in an example here, one of these electrons will split here, the other one goes on to this chlorine. So we're forming 2 chlorine radicals with the initiation of light. And this chlorine radical that forms can join up with a radical from the H and this form here. And now we've formed H and the Cl with the CH3 leftover radical. And then that can react with another molecule of chlorine to form the chlorine radical. And now we formed a bond to CH3Cl. There's many different possible termination steps that can occur. 2 chlorine radicals can get together to form a new molecule of chlorine. A chlorine radical plus a CH3 radical can get together, or 2 CH3 radicals can get together to form ethane. So polar reactions typically occur between something that's positively polarized and negatively polarized. So we have an opposites attract situation here. Negative charges are attracted to positive charges. Electron-rich species are attracted to electron-deficient species. An example of one of these is chloromethane. As we have that chlorine up on top, that's electronegative. That makes the carbon electropositive. So this is going to be electron poor, that carbon there, whereas the chlorine is electron-rich. And then we have methyl lithium. Now we've changed what's attached to the carbon. It's now a lithium ion, so that's very positively charged, and that makes carbon negatively charged. So these two are attracted to each other because one is electron poor, which is the chloromethane, and then a methyl lithium is the electron-rich one. And this table here will show you the different patterns in functional groups, and you can see typically what's acting as an electron-poor compound and also what's going to be electron-rich. The functional groups involving carbonyls tend to be electron-poor. These are electron-rich. Alkyl halides are electron-poor. And then alkenes, alcohols, amines, ethers, thiols, nitriles, these ones tend to be electron-rich as well. So in a polar reaction here with methanol, methanol is weakly electron-poor. We can see that small little bubble of red there. So this is weakly poor. But if we protonate that alcohol and make it H+, that is going to make it strongly electron-poor. And one of the qualities that helps in these reactions is that a molecule can be made to be polarizable, which means it can spread its electron density. And we mentioned before, electron-rich molecules like to react with electron-poor molecules. So things that are mediocre, OH and an SH, these are less polarizable. They're not as electronegative as the halides. These ones are more polarizable. So Cl and I are more electronegative. They're also larger molecules, so they can spread the electron density around much better. A nucleophile is an electron-rich species and can donate electron pairs. And more polarizable nucleophiles equal a stronger nucleophile. And these are typically negative or they are neutral. So in the situation of this OCH3 minus here, this is negatively charged. So these electrons from here on the negative charge can grab a hydrogen and the electrons go on to the bromine. So we now have this extra pair of electrons, a negative charge on the bromine. The O has formed a new bond to H. So here's my new bond. My product now is neutral. Electrons always move from a nucleophile to an electrophile. So we're going from the negative to hook into the positive. An electrophile is an electron-deficient species that can accept a pair of electrons. Carbocations and partially positive atoms are typically electrophilic. These can be neutral or they can be positive. So our neutral here, this is my nucleophile. This is my electrophile because it is positive. My electrons are going from the nucleophile or from the negative thing to the positive thing. Those electrons will go here when that grabs the H. And this becomes positively charged. So now I've added a hydrogen right there. There's my new bond. And in the process, I've created water. So reminder, electrons always move from a nucleophile to an electrophile. So here are some different nucleophiles on top. You can see the electron density mapping shows that it's very red or partially red. The ones that are very, very red have negative charges. So these on top are my nucleophiles that are electron rich. Ammonia and water have a little bit of red, and that is due to the electronegative nitrogens, but they're only partially negative. That's why it's just a little bit red. So that's partially negative there. And then on the bottom, we have our electrophiles that are electron poor. So the blue one is the H3O plus that is positively charged, and these other ones are partially positive. And they're partially positive as a result of what they are bonded to. So that bromine and the oxygen are drawing electron density out of that carbon to make it partially positive. If we look at a couple of examples here, we're going to figure out which one is likely to behave as a nucleophile and which as an electrophile. So something that has a positive charge is electron poor. So this will be an electrophile. Something with a negative charge is electron rich, so this is a nucleophile. This one is neutral, so we're going to see what it's attached to. There's a nitrogen here, which is a lone pair. This one's going to act as a nucleophile. And a sulfur with 3 CH3 groups on here. This is positively charged. This is an electrophile. So in a typical reaction, if we're dealing with ethylene plus water that is exposed to an acid catalyst at 250 degrees, there's a couple of different arrows and mechanisms that work together here. And so what we're going to see is ethylene is going to act as a nucleophile. The water will become protonated by the acid. So this is going to act as our electrophile, which I'm going to abbreviate E+. So my nucleophile is going to grab a proton from the electrophile. So I've added an H. This becomes a carbocation. And there's also the water that was left behind. And now the water is going to act as a nucleophile because it's got lone pairs. The positive is going to act as an electrophile. My nucleophile is going to attack the electrophile. And I form a new bond here. And my oxygen is positively charged because it's making 3 bonds. And then to get to the product, another molecule of water is just going to pick up that hydrogen. So in the process, I formed ethanol. So what I just showed you are what we call curved arrows, and these are used to show how electrons move as bonds are breaking or they're forming. So these are the mechanisms. There's 4 different ways that we can move electrons in polar reactions. We've seen already how an acid and base mechanism works. The base is going fishing for the proton in the acid, which then becomes this new bond here, and we get the lone pair added onto the acid. The first one that we are looking at is a nucleophilic attack. Or if you would like to be less violent, we have nucleophilic hugs. And that is the case where a nucleophile is going to attack or hug an electrophile. The next type of curved arrow is the loss of a leaving group. And this is going to result in a leaving group that leaves. We have a proton transfer, which is the one we just drew. This typically happens in acid-base reactions. And a lot of times it's abbreviated as plus minus H. And our last one is a rearrangement. So in the first, we have a nucleophilic attack. We have pi bonds that can also act as a nucleophile other than just some things that are negative or positive. So I have a nucleophile in the form of the benzene ring. These electrons can attack this sulfur. This will result in a loss of electrons here and a new bond to S. Form that, and then if I get a nucleophilic attack, we get a hydrogen here, positive here, and then the Cl minus. So only one of the carbon atoms from the pi bond uses the pair of electrons, and the other one becomes a carbocation. We have a loss of a leaving group. This is a bond cleavage, and one of the atoms or groups takes the pair of electrons. So here my bromine is acting as the leaving group because it's electronegative and can take on the pair of electrons. It's okay with having an extra lone pair. So the bond between the C and the Br are going to break, and the electrons are going to go to the Br, which results in a carbocation, plus the Br now has an extra pair of electrons. So we can have a one arrow where the leaving group leaves, or it can be common for more than one curved arrow to show loss of a leaving group. So in this example here, the lone pair electrons from this oxygen can come down, and there should be another pair of electrons right there. So that's missing. So these electrons come down here to form a double bond between the N. That will shift these electrons into here. This goes into here, and then my Cl, which was my leaving group, will leave. So my new bonds that formed are here, there. The positive is still on the nitrogen, and I form a double bond there, and then my leaving group was the Cl minus. We have a proton transfer, which we saw earlier in chapter 3. This requires two curved arrows. So my oxygen lone pair is going to grab the hydrogen, and the electrons from the HO bond are going to go on to the oxygen. So my oxygen now gets protonated with the H, and it's positive, and in the process we formed water. And one of those lone pairs, if you draw both, came from that bond. The deprotonation of a compound is sometimes shown with just one arrow, so we might just have something like that, and then we get the oxygen. Sometimes we need multiple arrows to show all of the steps wherein a proton is being exchanged. So if I have an OH minus, that's going to grab the proton, and those electrons will go on to this carbon. And then we get a negative charge there. And if we want it, we can draw a resonance structure. These electrons can go into here to form a double bond, and those electrons go up top. So I have an extra lone pair of electrons on the oxygen, and my double bond is here. So these are curved resonance arrows. And then we had the protonation step that happened in the first step with the OH minus. Rearrangements can happen if we have carbocations involved, and carbocations can be stabilized by neighboring groups through some orbital overlapping called hyperconjugation. So if we have a methyl group that's a carbocation, this is not very stable. At least when the C is on the plus, but it can kind of, through spirit, can donate some of that positive charge or spread it out over the carbon next to it. So it can donate it into the empty p orbital there. So when we do substitution reactions, this can increase the stability of a carbocation due to the number of adjacent sigma bonds that's aligned with the empty p orbitals. So pretty much what that is saying is as we increase the substituents on a carbocation, that's going to make it more stable. A methyl carbocation is not very stable because it can't spread out that electron positive charge. If we add one R group, this is a primary carbocation, we have one more place to spread out the positive charge. Secondary, there's 2 spaces to spread out the positive charge, and on the tertiary we have 3. So as we add more groups, this is increasingly stable. So there's 2 types of carbocation rearrangements that are common. One is the 1,2 hydride shift. And in that case, the hydride moves from this carbon here to another. So that's a 1,2 hydride shift. So there's my carbon skeleton before. I'm going to take that H and I'm going to move it to this side over here. So that fulfills this secondary carbocation. The carbocation then moves to the tertiary, which is more stable. And in this case, we have a 1,2 methide shift. So this whole CH3 group is going to move over to this carbon. So my CH3 is here now. This was a secondary carbocation. And because I took the carbon out of that carbon, this is now a tertiary carbocation, which again is more stable. The shifts can only occur from a carbon next to it. So it's not going to move 2 carbons away, and it will only occur if we can make a more stable carbocation. So in this reaction, what product would you expect from acid catalyzed reaction of cyclohexene with water? And if we're drawing the mechanisms here, we have a proton transfer. So I'm going to abbreviate that plus minus H. So one carbon gets the hydrogen, the other gets the positive charge. And in the process of this grabbing the H, I also created OH minus. This is a nucleophile because it's negative. My positive charge is the electrophile, so now I can have a nucleophilic attack. So this H is still here, and I've formed now a new bond to the OH. So that is the product I would get in that reaction. Okay, here an acid catalyzed reaction of water with 2-methylpropane yields 2-methyl-2-propanol. What is the structure of the carbocation formed during the reaction? Show the mechanism. Just like the last one, we're going to start with a proton transfer. And my electron pair from the pi bond is going to grab a hydrogen. The H will go here, and I'm going to form this carbocation because that one's more stable. So I don't form this one. This is a no because it's less stable. So tertiary carbocation is more stable. So that was my proton transfer, and I formed OH minus in the process. This is acting as my nucleophile. The positive is my electrophile. And so there is the product that forms, which we see here. So this is the new bond that forms. It looks a little bit different, but if we go to name it, it's the same thing. The arrow pushing shows us how the reactions happen, and this allows us to memorize all of the reactions lists if we can remember the 4 different types of arrow pushing mechanisms.